This is a joint work with Mark Braverman and Matt Weinberg. So let me start with some definitions and backgrounds. So in a combinatorial auction, there are m bidders, m items, and each bidder has a valuation function which is non-negative and monotone. And in this talk, we are particularly interested in the XOS valuations. So it is between submodular and subadditive. The definition is the following. XOS valuation V can be specified by a bunch of additive valuations, AIs. We also call AIs the clauses of V. And for V, the value on the subset S is just the maximum over all clauses value on S. Okay. And in this talk, we are the auctioneer, and our goal is to maximize the social welfare. And we're interested in the following question. Choose for mechanisms as powerful as algorithms. So in an algorithm, the bidders have no incentive, and they will just follow the algorithm. Okay. So let's see what is known. First of all, the answer is yes if we make no restriction on the computation, because VCG is truthful, it maximizes social welfare. However, it requires exponential computation or communication. And if you are interested in computationally efficient ones, the best known truthful mechanism achieves 1 over square root of log m approximation. And on the other hand, for negative result, truthful mechanisms with polynomial running time or polynomial number of value queries can get at most 1 over m to the omega of 1 approximation. So if you look at these two results a little bit, you feel they seem to contradict with each other because 1 over m to the omega of 1 is smaller than 1 over square root of log m. The reason is that technically the mechanism in the first result is not computationally efficient because it uses demand query, which is NP hard, or it requires an exponential number of value queries. However, demand query is very natural, and if the bidders have succinct representation of their valuations, they should be easy, like they should answer demand query very fast. So if we are interested in truthful mechanisms with demand queries, the computational complexity is not the right model. That is why the communication complexity is considered. And in this setting, the communication complexity basically cares about the number of bits transmitted between the auctioneer and the bidders. Okay? So truthful mechanisms with a polynomial number of demand queries will be included in the set of truthful mechanisms with polynomial communication cost. That's why we focus on truthful mechanisms with polynomial communication cost. And what is the best known result? Okay. So for truthful mechanisms, it's just a result I showed you in the previous slide. For algorithms, so here we use the word protocol instead of algorithms because we care about communication. The best known protocol get 1 minus 1 over E approximation, and it is tight. Okay. So notice there's a gap between the best known results. However, there's no separation proved. And in a recent work by Dobzhinsky, he showed the potential way to prove the separation. So one application in his work says the following. In a two-party combinatorial auction with XOS bidders, an alpha approximation truthful mechanism with polynomial communication costs will imply an alpha approximation simultaneous protocol with polynomial communication costs. So I explain what is a simultaneous protocol in the next slide. So basically, this result says that a negative result on simultaneous protocols will imply a negative result on truthful mechanisms. Okay. So what is a simultaneous protocol in this setting? It's very simple. So bidder 1, we call her Alice, and bidder 2, we call him Bob. Just send some message to the auctioneer simultaneously. And after that, auctioneer needs to output the allocation. So there's no other interaction. Notice that we also call this problem allocation problem because later we will introduce another problem called the decision problem. And for now, you just need to remember this problem is called allocation problem because the auctioneer outputs the allocation. Okay. And speaking of simultaneous communication complexity, there are many known results giving the separation between simultaneous communication complexity and communication complexity. Even in the combinatorial auction setting, there's a proved gap. However, this gap is exponential in the number of players. And notice that we are interested in the two-bidder case. So this result does not work for our purpose. Okay. So these are the background. And now I can state the main problem considered in this work. For a two-party combinatorial auction with XOS bidders, what is the best approximation ratio that can be achieved by a simultaneous protocol with polynomial communication cost? Okay, so we are comparing to any arbitrary protocols that can be very interactive, and the best known result gets 3/4 approximation for the two-bidder case. This is the same as a protocol that gets 1 minus 1 over E for multiple bidders. Okay, it's also tight. So if we can show that the simultaneous protocol cannot achieve 3/4, then we will get a separation between choose-form mechanisms and the protocols. On the other hand, if we do get a good simultaneous protocol, then it might give us some ideas about how to design choose-form mechanisms because most choose-form mechanisms I've ever seen are not very interactive. And later in this talk, I'll show you a choose-form mechanism based on a simultaneous protocol in a restricted setting. Okay. So before I show you the results, let's first think about the problem a little bit. So first of all, it's not hard to get a half approximation because there are only two bidders. Even for choose-form mechanisms, because we can sell the entire bundle using a second price auction, and then we will get the maximum of Alice and Bob's valuation on the entire set. It's not hard to see it's a half approximation. So in order to beat half, we need Alice and Bob to send some sketch that contains more information about their valuations. However, there's a result that is against this approach in some sense, saying that a poly-size sketching scheme for XOS valuations cannot get better than 1 over square root m approximation for value queries. So means to get better than half is not trivial, but so to beat half, we need some different kind of sketch that does not approximate the value query everywhere, but it still contains enough information for the auctioneer to make the allocation. Okay. So actually, we can beat half, and we get 23 over 32 approximation. This is very close to 3/4, but not there. And if you allow us to make some relaxation on the problem, then we can get 3/4. So for example, if we change XOS to binary XOS, then we can get a 3/4 approximation. So what is a binary XOS valuation? Remember, in XOS valuation, the XOS valuation is specified by a bunch of additive valuations. And in binary XOS, all these additive valuations are binary, or you can consider as subsets of the items. Okay. And also, this 3/4 approximation protocol can be made into a choose-form mechanism. Also, if you allow me to use a 2-round protocol, then we can also get the 3/4 approximation. Okay. So these are the positive results. Because we did not get the 3/4 for the simultaneous XOS case, we also try to prove some negative results. And unfortunately, we did not manage to prove the negative result for the allocation problem. We only proved the negative result for the decision problem. So it's very similar to the allocation problem. The only difference is that instead of outputting the allocation, in the end, the auctioneer needs to decide whether the optimal social welfare is at least x or at most alpha times x. And if the optimal social welfare is between alpha x and x, then the auctioneer can output anything. So we show that for any simultaneous protocol with polynomial communication cost, they cannot get a 3/4 approximation for the decision problem, even for binary XOS bidders. Okay. So to compare with our positive result, only our second protocol does not work for the decision problem. And combined with a negative result, it is saying that in the second protocol, the auctioneer somehow outputs a approximately good allocation without knowing how good it is. Okay, so these are the results. Okay, now I'm going to tell you more details about the results. I'll start. Yeah.
So I don't understand. Usually you get an allocation, each player computes his valuation.
Yeah.
And then just add it. So what is the difficulty here?
So usually, like decision problem is easier than allocation problem. But here the problem is that it's a simultaneous protocol. So if you give me one more round, I can solve the decision problem. But yeah. So okay, I'm going to first show you two warm-up protocols that are easy to understand. Also, they are not trivial because they beat half approximation. So first is the protocol for binary XOS valuation. It's very simple. So recall Alice's valuation can be specified by a bunch of binary additive valuations. Then she just chooses 3 clauses from them. I'll tell you how to choose them in the next slide. And then she picks a random one and sends to the auctioneer. So remember the binary additive valuation, like for example, BJ can be considered as a subset of items. So the auctioneer just allocate that subset to the Alice and allocate the rest to Bob. And yeah, so this protocol is very simple. Bob even does not need to send any message. Okay? So now let me tell you how to choose this B1, B2, B3. So we will choose B1 to be the clause that maximizes its value on the entire set. So only reporting B1 will give a half approximation. It's not hard to see that. The problem of only reporting B1 is that if B1 is very close to Bob's valuation, then actually reporting B1 is a very bad idea. So therefore, we also report B2 and B3. So they are chosen using the following way. We do a mental experiment, and we think we are running another combinatorial auction on 2 copies of Alice. And we find the optimal allocation, and also let B2, B3 to be the corresponding clauses used in the optimal allocation. Okay. So the intuition is the following. If B2 is really very close to Bob's valuation, then B3 is actually something good to send. On the other hand, if B3 is very close to Bob's valuation, then B2 is something good to send. Okay. So this is how we choose BJ. And now I'm going to show you the actual proof. I promise this is the only proof in this talk. Okay. So we define SW to be the optimal social welfare for notation convenience, and let S and S bar to be the allocation that achieves the optimal social welfare between V1 and V2. And let the clauses that are binary additive valuations, A and A prime, to be the clauses using the optimal allocation. Okay. And we also define T and T bar to be the allocation that achieves the optimal allocation between B2 and B3. So optimal social welfare between B2 and B3. So this is the optimal social welfare on 2 copies of Alice. And then from the definition of B1, B2, and B3, we get these 2 inequalities. Okay. And the proof will be finished in the next slide. So the expected social welfare we get is the following. This is because when Alice sends BJ, actually we are getting the optimal social welfare between Bj and V2. This mainly comes from the fact that Bj is a binary additive valuations. And then we write down some specific allocations. So it's definitely smaller than the optimal social welfares. And the rest of the proof is just to pair things up. So notice that here we have B2 of T and B3 of T bar. And using the inequalities in the previous slide, we know this thing, this sum is the optimal social welfare on 2 copies of Alice. So we know that B2 of T plus B3 of T bar is larger than B1 of S bar plus A of S. And also notice that A prime is an additive valuation, so we can combine A prime T bar and A prime T to get A prime of the entire set. Okay. Then again, we combine things. So here, B1 is also additive, so we combine B1 of S and B1 of S bar. And we get B1 of the entire set is larger than A of S. So finally, we get the 2/3 of the optimal social welfare. Okay. So this is a proof. Okay. Now I'm going to show you another warm-up protocol for the XOS valuations. It's very similar to the previous protocol. Okay. So Alice still chooses these 3 clauses, but this time Bob also needs to do something. So he also chooses 3 clauses from his valuation in the same way. And they send all these clauses to the auctioneer simultaneously. And then auctioneer finds an allocation that maximizes the social welfare between these clauses and allocates the item according to it. Okay. So compared with the previous protocol, in the previous protocol, the auctioneer allocates item I to Alice if the clause she sent likes the item. Notice that this thing can be only done if the valuation is binary XOS, because you can define what does like means there. Now, like if the valuation is XOS, it's not clear which item Alice likes. So we also need information from Bob to make the allocation. And therefore, this protocol gets worse approximation ratio. It only gets 3/5, and the previous one gets 2/3. However, in this protocol, the auctioneer gets some ideas about how good is the allocation, because she actually computes this thing. So this protocol also works for the decision problem. Okay. So now I'm going to show you the actual protocol that gets our best approximation ratio. So the main component in the protocol is we call K alpha sketch. It's basically K different clauses, not different, K clauses from the valuation, and we first need to define xi to be the fraction. Oh, sorry. Also, here I'm only going to define the sketch for the binary XOS valuations because it's easy to understand, and the sketch for the XOS valuation will be very similar. Okay, so we define xi to be the fraction of clauses who like item I in the sketch. Okay. And the K alpha sketch is just the K clauses from the valuation that maximize this term. Okay. So let's understand this term intuitively. So remember, because the valuation is binary XOS, each clause can be seen as a subset. And here, the sum of xi is just the average size of the subsets in the sketch. So we definitely want this thing to be large. But we also have this term minus alpha xi squared. It's used to force the sketch to choose different clauses from the valuation. Okay. So to compare with the warm-up example, the B1 is just the 1, half sketch, and B2, B3 are the 2, half sketch. Okay. So our actual protocol for binary XOS will be the following. We just run the warm-up protocol, and we replace the B1, B2, B3 by the K half sketch. Okay, this is the only difference. And this protocol will give us a 3/4 minus 1/k approximation. Okay. So notice that the communication cost does not depend on K, so we can actually take K to be infinity. So this protocol will give you exactly 3/4 approximation. And this protocol can also be made truthful because it's like simultaneous and very simple. So we just run this protocol, and in the end, we charge, for each item allocated to Alice, we charge her xi over 2. And it can be proved that it's a strictly dominant strategy for Alice to report a K-half sketch. Okay, notice here the strictly is very important because technically any protocol for binary XOS can be made truthful if you charge price 1. Because in that case, the utility of the bidders are always 0 and they can be forced to do anything. Okay. So finally, it's our protocol for XOS. We still use the warm-up protocol, and we replace B1 to B6 by the K1/3 sketch. And this protocol will give us a 23/32 minus 1/k approximation. And notice here, we cannot take K to be infinity because communication cost depends on K. So, but still, we can make it to be poly-M. It's fine. One more thing to notice that this protocol is deterministic, unlike the previous one. Okay. So these are the positive results. One more thing to mention is that we have an example that this protocol can get at most 23/32 approximation. So in order to improve this approximation ratio, we need better ideas. Okay. So now I'm going to show you some ideas about the negative result. Recall that our negative result is on the decision problem. And in the decision problem, you need to decide whether the optimal social welfare is large or not. And the way we prove such a negative result is by constructing a distribution of input such that with probably half, the optimal social welfare is large, and with probably half, the optimal social welfare is small. And so any protocol with polynomial communication cost cannot distinguish these two cases with a probability much better than half. Okay. So I'm going to show you the actual construction of the input. It's a little bit technical. So we first get two random set S and T. Their size are m/2, and their intersection has size m/3. These are not the clauses for them. And then Alice gets exponential many random clauses such that each of them has size m/2, and the intersection with S has size m/3. Same for Bob and T. So notice that the optimal social welfare between all these random clauses are small with high probability. So these clauses don't affect the answer to the decision problem. Okay. And then we also give Alice and Bob some special clauses, U1 and U2. They all have size m/2. And in case 1, U1 is the complement of U2. So they are in red in the picture. Okay. And in case 2, U1 equals U2. They are in purple in the picture. And we can also prove that with high probability, the optimal social welfare between U1 and random clauses of Bob is small. Same for U2 and random clauses from Alice. So it's basically saying the answer to the decision problem is only dependent on whether we are in case 1 or case 2. Okay. Finally, notice that our construction makes U1 looks very similar to all the other random clauses of Alice. So actually, Alice cannot distinguish U1 from other clauses. And because her message has polynomial size and there are exponential many random clauses, so Alice won't be able to send enough information about U1. So same for Bob. And the auctioneer needs enough information to about U1 and U2 to distinguish between the two cases. So intuitively, auctioneer cannot solve the decision problem. And the actual proof uses information theory. It just follows the intuition. Okay. So to summarize, in this work, we get almost tight or tight protocols with very limited interactions, and the second one can be made into a truth-form mechanism. Also, we get a lower bound for the decision problem, so it shows a gap between the decision problem and the allocation problem. And it also tells you that if you really want to get a 3/4 approximation for the allocation problem, in your protocol, the auctioneer needs to allocate the item without knowing how good it is. Okay. So for open problems, so this work tells us that the best approximation ratio is between 23/32 and 3/4, but we still don't know the answer. So it's still interesting to figure out what is the right answer. And the second one is that we want to know if we can get the better than half approximation truth-form mechanisms for two-party combinatorial auctions with XOS or even submodular bidders. Notice that in this work, we get the 3/4 approximation for binary XOS bidders. Okay, thank you.